For Andrew, Kate, and I's system, we decided to do the fluid system analysis of a Catit water fountain. For a little bit of an overview, this can be used wherever there is an outlet and is accessible to your pet. The power requirement for this is for the pump to cycle the water. This allows cat constant access to filtered and refreshed water throughout their day. So how does this system work? Water in the system is pumped from the bottom of a reservoir up the tube to the top of the fountain. And this is where the water exits from the top of the fountain and where the cat can then access it. Then water is caught in the green basement below, where it percolates through a filter via gravity back into that main reservoir to repeat the cycle again. To start from our session 2, we calculated pressure forces on planes and curved surfaces in our system. We identified the plane surface as the bottom of the basin and the curved surface as a quarter of the area of the wall of the basin. You can see those highlighted in our diagram. We assumed our system to be a cylinder, and we found all of the necessary values for those calculations. Then to find the force on the plane surface, we used the formula for force that includes the specific weight and area as well as HC. The specific weight is 9,810 newtons per meter cubed. The HC value based on the height is 0.0866 meters, and the area of the bottom is 0.0346 meters squared. With all of that, we found that the force on the bottom is 29.39 newtons. Then we analyzed the curved surface. We found the vertical and horizontal projections, and we ended up using the X and Y projections since the surface was already vertically oriented. The forces were the same each at 3.85 newtons in magnitude. And given that information, the magnitude and direction of the resultant force is 5.45 newtons at 45 degrees.
For our continuity equation, we assumed that 3 liters of water would cycle through the system per hour, giving us a volumetric flow rate of 8.33 times 10 to the negative 7 meters cubed per second. Our fluid in the system was water, so it's incompressible with a density of 1,000 kilograms per meters cubed. Our point 1, we took that as equal to the level in the main reservoir where the tube starts that will be used to pump the fluid up to the top. And then our point 2 was at that top of that pipe where the water would come out for the cat to drink it. We found our areas for each of those points using the official Catit sites and determining the ratios in the diagrams they provided. Our mass flow rate we found by multiplying the density times our volumetric flow rate for 8.3 times 10 to the negative 4th kilograms per second. And then our velocities at point 1 and point 2 are relatively simple to find. We rearranged the continuity equation of Q equals VA to get velocities equal to the volumetric flow rate divided by the area. And then we just divided our previously found volumetric flow rate by the area at point 1 and point 2. So the velocity at point 2 was 0.001 meters per second, and our velocity at point 1 was 0.001. Point 2 was 0.001 meters per second, and our velocity at point 1 was 2.44 times 10 to the negative 5th meters per second.
We then apply the work energy equation to the system, where we assume the same height difference and same volumetric flow rate as the continuity equation. We first started with calculating the pressure at point 1, which is the hydrostatic pressure. And we assumed that the fountain is completely full of water, so the height that we used would be 0.132 meters. We assumed that the pressure at the second point is 0 because it's a free jet. And there is no head extracted in the system because there is no turbine present, only a pump. And there is no head loss because we assume that there is no friction in the system. So our first step was to use the work energy equation to find our useful head, which turned out to be 5.1 times 10 to the negative 8 meters. We then used that useful head and implemented it into the power equation in kilowatts, which we got 2.19 times 10 to negative 2.91 times 10 to negative 13 kilowatts, which is also equal to 2.91 times 10 to negative 10 watts. And finally, for our potential improvements, this system is very small and simple, so we couldn't really think of anything except for increasing the efficiency of the pump, so less power is required to apply the same useful head.